Imagine a cosmic object so strange it makes black holes look ordinary. Something that doesn't pull everything in, but violently throws everything out. A place where time itself might run backward, where the laws of physics flip inside out, and where the very fabric of reality behaves in ways that challenge everything we think we know about the universe. This is a white hole. They exist perfectly in Einstein's equations. They're the mathematical mirror image of black holes, predicted by the same theory that revealed black holes decades before we actually found them. Yet we've never seen one. Not a single confirmed observation in the entire cosmos. Which raises an unsettling question: are white holes real objects waiting to be discovered, or are they beautiful mathematics that nature simply chose not to use? To understand what makes white holes so bizarre, you first need to grasp what they actually are. Picture a black hole, that gravitational monster from which nothing can escape. Now play the film backward. Matter and light aren't falling in. They're erupting outward. The event horizon isn't a point of no return for things going in, but an impenetrable barrier preventing anything from entering. You can't fall into a white hole no matter how hard you try. You'd be repelled, pushed away by forces that become infinite at the boundary. From a distance, a white hole would look almost identical to a black hole. Same mass. Same gravitational pull on distant objects. Same warping of spacetime around it. A crew watching from their spaceship wouldn't immediately notice the difference. They'd see the same swirling accretion disk, the same distorted starlight bending around the edge. But then they'd witness something impossible for a black hole. A sudden eruption. Material blasting outward from the center, as if the universe itself were vomiting matter and energy into space. The mathematics behind white holes emerged in 1916, just months after Einstein published his general theory of relativity. Karl Schwarzschild, a German physicist serving on the Russian front during World War I, found the first exact solution to Einstein's field equations. He was calculating how spacetime curves around a massive object, trying to understand what happens near something incredibly dense. What he discovered changed physics forever. But here's what most people don't know about Schwarzschild's solution. It actually contains two objects, not one. The equations don't care which direction time flows. Flip time backward in the mathematics, and you get a perfect mirror image. Where the black hole pulls everything toward a future singularity, the white hole spits everything out from a past singularity. Both solutions are equally valid according to Einstein's equations. Both are permitted by the fundamental laws governing spacetime. This symmetry is stunning when you think about it. General relativity treats time as just another dimension, one that can be traversed forward or backward in the mathematics. The equations themselves don't prefer one direction over the other. So if nature allows matter to collapse into an infinitely dense point that traps everything behind an event horizon, why shouldn't it also allow the opposite? A point that existed in the past, one that expelled everything and permits nothing to enter. The problem is formation. We know exactly how black holes form. A massive star runs out of fuel. Nuclear fusion stops. Without the outward pressure from fusion to counteract gravity, the core collapses catastrophically. The outer layers explode as a supernova while the core compresses beyond any stopping point. If enough mass remains, not even atomic structure can resist the crush. Protons and electrons merge into neutrons. Then even neutron degeneracy pressure fails. The collapse continues until all that mass concentrates at a single point, creating the black hole's singularity. But run that process backward and it stops making sense. You'd need matter to spontaneously explode outward from a point of infinite density, organizing itself into stars and planets and galaxies. It's like watching an egg unscramble itself, or shattered glass reassembling into a perfect window. The second law of thermodynamics screams in protest. Entropy doesn't decrease on its own. Disorder doesn't spontaneously become order without energy input from somewhere. This is where the white hole concept gets truly strange. If they can't form from stellar collapse, where would they come from? One possibility: they've always existed. Perhaps white holes are primordial objects, cosmic relics that emerged during the Big Bang itself, when the universe was young and the laws of physics operated under extreme conditions we barely understand. In those first fractions of a second, when all of spacetime was compressed to quantum scales, maybe white holes could form naturally. Recent theoretical work suggests something even more radical. What if black holes transform into white holes? Not immediately, but after an incredibly long time, through quantum processes that general relativity alone can't capture. This idea comes from loop quantum gravity, one of the leading attempts to merge quantum mechanics with Einstein's theory of spacetime. The mathematics suggests that when a black hole shrinks down to extraordinarily small sizes, approaching what's called the Planck scale, quantum effects take over completely. At that point, the singularity at the black hole's center might not be an ending at all. Instead, spacetime could tunnel through to a new state. The black hole could flip, transforming into a white hole that begins expelling everything that fell in. This wouldn't happen instantly from our perspective. Due to the extreme time dilation near black holes, billions of years could pass outside while mere microseconds tick by at the center. The black hole might appear eternal to us, but from the inside perspective, the transformation happens quickly. Carlo Rovelli, one of the founders of loop quantum gravity, has been developing this white hole hypothesis for years. He argues that the singularity problem, that troubling point of infinite density where our equations break down, gets resolved by quantum gravity. Instead of matter crushing to an infinitely small point, quantum fluctuations prevent the final collapse. Space and time don't end. They transition into a white hole geometry, where matter can only move outward. This idea addresses one of the deepest mysteries in theoretical physics, the information paradox. When matter falls into a black hole, what happens to the information it carries? The quantum states, the precise arrangement of every particle, the complete physical description of everything that fell in. Black holes appear to destroy that information, which violates a fundamental principle of quantum mechanics. Information can't simply vanish from the universe. But if black holes eventually become white holes, the information returns. Scrambled, mangled beyond recognition, but preserved. Everything that fell into the black hole eventually erupts from the white hole. The universe doesn't lose information. It just gets processed through the most extreme transformation imaginable, a journey through a quantum spacetime transition that takes matter to the very edge of physical law and back. Here's where it gets even stranger. The transition from black hole to white hole creates what physicists call a Planck star, a configuration where matter reaches maximum compression before bouncing back. This object would be unimaginably small, far tinier than an atom, yet it would contain the entire mass of the original black hole. And because of relativistic time dilation, this object exists in a weird temporal state. From outside, it appears to last for billions or trillions of years. From inside, the bounce happens almost instantaneously. Now you're probably wondering about the most obvious question. If white holes are real, why haven't we seen them? Where are they hiding? Massive white holes formed from solar mass black holes would take longer than the current age of the universe to complete their transformation. We wouldn't expect to see those yet. But the early universe might have created countless tiny primordial black holes, some no larger than subatomic particles, formed from density fluctuations in the first moments after the Big Bang. These microscopic black holes would evaporate much faster through Hawking radiation. As they shrink, they'd reach the quantum transition point sooner. Some might have already transformed into white holes billions of years ago. They'd be incredibly small, with event horizons measured in Planck lengths, but they'd still carry mass. Lots of them scattered throughout the universe could collectively add up to significant gravitational effects. Which brings us to one of the most intriguing possibilities. Could white holes explain dark matter? We know something invisible is out there, providing extra gravity that holds galaxies together and bends light in ways visible matter alone can't explain. What if that something is a cosmic population of tiny white holes, primordial objects that formed in the universe's infancy and have been quietly existing ever since? They'd have mass. They'd exert gravity. But they'd be nearly impossible to detect directly because they're so small. The evidence, if it exists, might be hiding in plain sight. Some researchers have proposed that certain gamma-ray bursts, those mysterious explosions of high-energy light that appear randomly across the sky, could be white hole events. When a black hole finally transitions to a white hole and expels its contents, the process might be violent. Instantaneous from one perspective. All that accumulated matter and energy erupting in a single pulse. One particular gamma-ray burst, GRB 060614, caught astronomers' attention in 2006. It had properties that didn't fit the standard models. Long duration but no supernova signature. Appearing in a region of space with very few stars. The characteristics matched what you'd expect from a white hole explosion better than any conventional explanation. Not proof, but suggestive enough to keep scientists looking. What makes this hunt so challenging is that white holes and black holes would look nearly identical from afar. Both curve spacetime the same way. Both have event horizons. Both possess mass and possibly spin. The crucial difference only becomes apparent when you watch what they do over time. Does matter fall in and disappear? That's a black hole. Does matter erupt outward? That's a white hole. But catching that moment requires incredible luck and the right instruments pointed at the right place at exactly the right time. The mathematics of white holes reveals something profound about the nature of reality. Einstein's equations don't just describe what is. They describe what's possible within the framework of spacetime geometry. White holes are possible. The math is unambiguous about that. Whether nature actually implements every mathematical possibility remains an open question, one that cuts to the heart of how physical law relates to physical existence. The story gets stranger when you consider what it means for something to be mathematically real but perhaps physically impossible. White holes exist in the equations with the same certainty that black holes do. Carl Schwarzschild discovered both solutions simultaneously in 1916, just months after Einstein published general relativity. He was solving for how spacetime curves around a massive object, and the math gave him two answers. One where nothing escapes. One where nothing enters. Perfect symmetry in the language of geometry. But mathematics doesn't care about causality the way the physical universe does. You can write an equation that runs backward in time just as easily as one that runs forward. The numbers work. The logic holds. Yet we never see eggs unscramble themselves or shattered glass spontaneously reassemble. The universe has a direction, an arrow of time that points stubbornly forward. That asymmetry might be the only thing standing between black holes being commonplace and white holes being absent. Some physicists argue this is precisely why white holes can't exist in our universe. The cosmos emerged from the Big Bang with a particular orientation in time. Forward motion became encoded into the fabric of reality itself. Black holes fit naturally into this framework because they represent the future, the ultimate endpoint where matter goes to stay. White holes would represent the past, objects that existed from the beginning and eject their contents into the future. In a universe that started from a singular moment and expands eternally forward, only one of these solutions gets to be real. But that argument assumes the Big Bang wasn't itself a white hole event. Think about what happened in the first moments of cosmic history. Infinite density concentrated at a point. Then suddenly, violently, everything erupting outward. Matter, energy, spacetime itself exploding into existence. That's precisely what a white hole does. The entire observable universe might be the interior of a white hole that formed 13.8 billion years ago, and we're living in the aftermath of its one and only emission event. This gets to something deeper about how we understand the connection between theory and observation. White holes challenge our assumptions about what makes something scientifically valid. Usually, we demand experimental evidence. Show me the data. Point the telescope at it. Measure it repeatedly. But some aspects of reality might be fundamentally unobservable while still being absolutely real. Quantum mechanics already showed us this with particle behavior between measurements. General relativity might be teaching us the same lesson with white holes. The Schwarzschild solution describes an idealized, eternal black hole that has existed forever and will exist forever. No real black hole matches this description. Every black hole we know about formed from something, a collapsing star, merging compact objects, primordial density fluctuations. They have histories. They change over time. The mathematical solution doesn't account for formation, only for the final state. White holes face the opposite problem. The math describes the final state perfectly but offers no mechanism for how you'd get there. Creating a white hole from scratch seems to require conditions that violate everything we know about how matter and energy behave. You'd need to arrange mass and spacetime in a configuration where outward flow becomes mandatory, where the geometry itself forbids anything from entering. Stellar collapse can create the inward version naturally. Gravity does the work. What process creates the outward version? Conventional astrophysics has no answer. Unless the answer is quantum mechanics operating at scales where spacetime itself becomes uncertain. Loop quantum gravity suggests that space isn't smooth and continuous but granular at the smallest scales, pixelated into discrete units called Planck lengths. At this fundamental level, the rules change. Singularities can't form because there's a minimum possible size. When a black hole shrinks small enough through Hawking radiation, it reaches a point where quantum effects dominate completely. The fabric of spacetime starts fluctuating wildly. And in those fluctuations, a transition becomes possible. Carlo Rovelli describes it as quantum tunneling on a cosmic scale. Imagine an electron jumping between energy levels in an atom. It doesn't travel through the space between. It simply appears in the new state because quantum mechanics allows it. A black hole at Planck scale might do something similar, tunneling through a barrier that classical physics says is impossible, emerging on the other side as a white hole. The probability isn't high. But it's not zero. And given enough black holes over enough time, even unlikely events become inevitable. The transition point gets called a Planck star. Not a star in the conventional sense, but a configuration where matter reaches maximum compression before quantum pressure halts the collapse. Inside the black hole's event horizon, Hidden from external observation, the singularity gets replaced by this quantum structure. Time dilation becomes so extreme that what happens next depends entirely on your perspective. For someone falling in, the transition might take microseconds. For someone watching from outside, it could take billions of years or longer. This creates a bizarre situation where the same object exists as both black hole and white hole depending on when you observe it. Right now, what appears to be a black hole swallowing matter might contain a white hole interior that's already transitioned, already begun its outward phase. But because of how time dilates near the event horizon, that information hasn't propagated out yet. Won't propagate out until the distant future when the black hole has evaporated away and the white hole phase becomes observable. Which brings us back to the primordial black holes scattered throughout the cosmos. If they exist, and if loop quantum gravity is correct, some percentage of them should have already completed the transition. They'd be white holes right now, actively existing in the present moment. Microscopic objects with enormous mass density, emitting radiation, contributing gravitational effects. Completely invisible except through their influence on surrounding matter and light. Starting to sound familiar? Dark matter needs to be something that has mass, doesn't emit light, doesn't absorb light, and exists in vast quantities throughout the universe. White holes transformed from primordial black holes check every box. They'd cluster in galaxies the same way dark matter does. They'd provide the extra gravity needed to explain galactic rotation curves. They'd bend light through gravitational lensing. And they'd be nearly impossible to distinguish from empty space unless you caught one in the act of emitting something. The numbers potentially work. Estimates suggest primordial black holes could have formed with a wide range of masses, from subatomic to stellar scale. The smallest ones would evaporate fastest. Medium-sized ones might be transitioning now. Large ones would still appear as ordinary black holes. If even a small fraction of dark matter consists of white holes, that's enough to solve one of cosmology's biggest mysteries while simultaneously validating quantum gravity theories. But we need evidence beyond theoretical consistency. We need something observable, measurable, repeatable. Gamma-ray bursts remain the most promising candidate. These explosions appear randomly across the sky, releasing enormous energy in seconds or minutes. Most have known causes. Colliding neutron stars. Collapsing massive stars. Standard astrophysical processes. But some don't fit the models. They happen in unexpected places. They lack the signatures we'd expect. They remain genuinely mysterious. GRB 060614 stood out immediately. Long duration meant it should have come from a supernova. But no supernova appeared. Short duration gamma-ray bursts come from mergers. But this one lasted too long for that explanation. It originated from a region with few stars, making any stellar process unlikely. The energy output matched predictions for what a white hole transition might produce. All that mass and information stored inside a black hole, suddenly released in a single pulse as spacetime geometry inverts. Not proof. Correlation isn't causation. But it's enough to justify looking harder. Enough to motivate better instruments, more sensitive detectors, targeted searches for these anomalous events. If white holes are out there, if they're transitioning right now, we might be able to catch them. We might be able to watch spacetime turn itself inside out. The philosophical implications cut deeper than the physics. We're discussing objects that might exist in a state of permanent paradox. Observable yet hidden. Real yet impossible. governed by laws we've written down but don't fully understand. White holes force us to confront the limits of knowledge itself. Not just what we don't know yet, but what might be fundamentally unknowable given the structure of spacetime and the constraints of observation. You can't watch a white hole form because the formation happens in a black hole's interior, hidden behind an event horizon that nothing, not even information, can cross outward. You can only see the aftermath, the emission phase, assuming you're looking at the right place at the right time. And even then, distinguishing a white hole from other exotic phenomena requires precision measurements we're only beginning to develop. The universe might be full of them, and we'd never know unless we got extraordinarily lucky. Here's the thing about searching for something that might not want to be found. You need a strategy that accounts for your own ignorance. We don't know exactly what a white hole looks like when it transitions. We don't know how long the emission phase lasts. We don't know if it happens all at once or gradually. We're hunting shadows with a flashlight that might be pointing the wrong direction. But we're not completely blind. Physics constrains the possibilities. A white hole transition must conserve energy, momentum, angular momentum. It must obey causality within its local reference frame. It must produce detectable signatures if it interacts with surrounding matter or radiation. These constraints narrow the search space considerably. Start with energy. A primordial black hole transitioning to a white hole releases everything it ever absorbed. For a small black hole, that's not much mass. Maybe a few kilograms. Maybe less. But Einstein's equation tells us mass and energy are equivalent. A kilogram of matter converts to roughly 90 petajoules. That's 21 megatons of TNT equivalent. Released in seconds or minutes, that creates a gamma-ray burst easily detectable across cosmological distances. Larger primordial black holes carry more mass, produce bigger bursts. The relationship isn't linear. Double the mass, you get far more than double the energy release because the transition dynamics change. The interior geometry stretches further. The quantum tunneling probability shifts. The emission becomes more violent, more concentrated, harder to miss. Duration matters as much as intensity. A burst lasting milliseconds looks different from one lasting minutes. The spectral signature changes. The light curve changes. The way it interacts with intervening gas and dust changes. Each variation points toward different formation mechanisms, different source physics, different implications for whether we're seeing a white hole or something else entirely. Location provides another filter. White holes from primordial black holes should appear randomly distributed. They formed in the early universe when density fluctuations were nearly uniform. They've been drifting through space ever since, following gravitational flows, clustering slightly in galaxies but not concentrated in any particular region. A gamma-ray burst from a white hole could come from anywhere. Deep space. Galactic halos. Intergalactic voids. The randomness itself becomes a signature. Compare that to known gamma-ray burst sources. Supernovae cluster in star-forming regions. Neutron-star mergers happen in galaxies with older stellar populations. Active galactic nuclei sit at galaxy centers. Each source type has a preferred environment, a statistical pattern that emerges when you plot thousands of events. White holes wouldn't follow those patterns. They'd be the outliers, the unexplained dots on the map. GRB 060614 fits that profile perfectly. It came from a region with minimal star formation. No obvious host galaxy. No merger candidates nearby. Just empty space suddenly lighting up with gamma rays, then fading back to darkness. The burst lasted longer than typical short gamma-ray bursts but showed none of the supernova signatures expected from long bursts. It violated the standard classification scheme, forcing astronomers to create new categories just to file it somewhere. What if we stopped trying to fit it into existing categories? What if we treated it as evidence for something new, something the categories weren't designed to handle? The white hole hypothesis does exactly that. It predicts events that don't match supernova or merger templates because they're neither. They're quantum gravity phenomena, space-time inversions, the universe's most extreme phase transitions made observable. Testing this requires more than finding anomalous gamma-ray bursts. We need follow-up observations, multi-wavelength coverage, gravitational wave detectors listening for signals that might accompany the transition, neutrino observatories watching for particle emissions. The more independent measurements we have, the better we can distinguish white holes from imitators. Gravitational waves offer particularly strong constraints. A black hole to white hole transition should produce a specific waveform as spacetime geometry flips. The frequency depends on the black hole's mass. The amplitude depends on distance. The polarization encodes information about spin and charge. If we detect gamma rays and gravitational waves simultaneously from the same source, with waveforms matching white hole predictions, that's smoking gun evidence. Current gravitational wave detectors aren't sensitive enough for small primordial black holes. LIGO and Virgo target stellar mass sources. They'd miss the high-frequency signals from microscopic white holes entirely. But next-generation detectors could change that. Space-based observatories. Improved ground-based instruments. Detector networks that combine data from multiple sites to increase sensitivity and directional precision. Neutrinos add another layer. When matter emerges from a white hole, particle interactions should produce neutrinos alongside gamma rays. The ratio between neutrino flux and photon flux depends on the composition of emitted material, the temperature of the emission, the density of surrounding space. Measuring both simultaneously lets us reconstruct the physics of the source, testing whether it matches white hole models or points toward conventional astrophysics. The challenge is coordination. Gamma-ray telescopes, gravitational wave detectors, and neutrino observatories operate independently. They have different triggering systems, different response times, different fields of view. By the time one instrument alerts another, the transient event might be over. We need real-time data sharing, automated cross-checks, rapid follow-up protocols that activate within seconds of initial detection. Some of that infrastructure exists already. The gamma-ray coordinates network distributes alerts whenever satellites detect new bursts. Gravitational wave observatories issue public notifications during observing runs. Neutrino telescopes report high-energy events that might indicate astrophysical sources. The pieces are in place. We just need to connect them more tightly, reduce latency, improve coordination. But here's the deeper question. What if white holes don't produce dramatic explosions? What if the transition happens quietly, releasing energy gradually over years or centuries instead of seconds? Then we're not looking for bursts at all. We're looking for persistent sources that shouldn't exist according to standard astrophysics. Faint objects with unusual spectra. Things that glow steadily without obvious power sources. That's a much harder search. The sky is full of faint objects. Most are ordinary stars, galaxies, nebulae. Picking out white holes requires ruling out every conventional explanation first. You need accurate distances to calculate luminosity. You need spectroscopy to identify composition. You need time series data to check for variability. Each step filters the candidate list, but never to zero. There's always residual uncertainty, always alternative explanations that can't quite be excluded. Statistical approaches help. Instead of hunting individual white holes, look for population signatures. If millions of small white holes exist, their collective effects might be detectable even if individual objects remain hidden. They'd contribute to diffuse gamma-ray backgrounds. They'd add small perturbations to gravitational lensing statistics. They'd create subtle anomalies in cosmic microwave background data. The Fermi Gamma-Ray Space Telescope has mapped the entire sky in gamma rays multiple times. The data shows a diffuse background that can't be fully explained by known sources. Some comes from unresolved distant galaxies. Some from cosmic ray interactions. But there's excess emission, particularly at certain energies, that remains mysterious. Could that be white holes? Maybe. The spectrum roughly matches what you'd expect from a population of small transitioning black holes. But it also matches other exotic scenarios. Dark matter annihilation. Primordial magnetic fields. Unknown particle physics. Distinguishing between these requires better models and better data. Models that make precise predictions for how white hole populations would distribute across energy, time, and space. Data with higher resolution, better background subtraction, longer observation periods. The technology improves every year. Satellites get more sensitive. Analysis techniques get more sophisticated. We're reaching the point where definitive tests become possible. Gravitational lensing offers another avenue. White holes have mass. They bend light. If enough exist, they'd create a measurable lensing signal when background sources pass behind them. The effect would be tiny for individual events, but statistical analysis across millions of sources might reveal the pattern. Surveys like the Vera Rubin Observatory will image billions of galaxies repeatedly, tracking how their apparent positions and brightnesses change over time. That dataset could contain white hole signatures if we know how to look. The irony is that all this effort might prove white holes don't exist. That's a valid scientific outcome. Negative results eliminate possibilities, narrow the parameter space, force theories to evolve or die. If we search thoroughly and find nothing, that tells us something important about quantum gravity, about the early universe, about which mathematical solutions correspond to physical reality. But what if we find them? What if the next gamma-ray burst we detect carries unmistakable white hole signatures? What if gravitational waves and neutrinos confirm it simultaneously? What if follow-up observations rule out every alternative explanation? Then everything changes. Quantum gravity becomes experimentally verified. The information paradox gets resolved. Dark matter gains a new candidate. The early universe reveals secrets we can actually test. And the philosophical implications stretch beyond physics. Discovery would prove that reality operates on principles we've barely glimpsed. That quantum mechanics and gravity merge in ways our current theories only approximate. That the universe recycles information through mechanisms more elegant than we imagined. That spacetime itself is more fluid, more dynamic, more surprising than the rigid geometry we teach in textbooks. But here's where it gets really interesting. White holes don't just solve abstract theoretical problems. They might explain what we see when we look at the actual universe. Dark matter, for instance. The invisible substance that outweighs ordinary matter 5 to 1. We know it's there because galaxies rotate wrong. Because gravitational lensing bends light in patterns that visible matter can't explain. Because the cosmic microwave background shows density fluctuations that require extra mass. But nobody knows what it is. Dozens of candidates have been proposed. Weakly interacting massive particles, axions, sterile neutrinos, modified gravity theories. Each has problems. Each fails some observational test or requires fine-tuning that feels contrived. White holes offer a different answer. If primordial black holes formed in the early universe and transitioned to white holes after billions of years, their properties match dark matter requirements almost perfectly. They have mass. They don't emit light. They interact only through gravity. They're stable on cosmological timescales. And the math works. Loop quantum gravity calculations suggest the number density and mass distribution could match dark matter observations if the initial population of primordial black holes had the right characteristics. You can test this. Dark matter halos have specific density profiles. They cluster in particular ways. They affect structure formation through precise mechanisms. If white holes constitute dark matter, they'd leave signatures different from particle candidates. Subtle differences in how galaxies form, how clusters evolve, how large-scale structure develops. Current surveys are reaching the sensitivity needed to detect those differences. The Dark Energy Survey, the Sloan Digital Sky Survey, upcoming missions like Euclid and the Nancy Grace Roman Space Telescope. They're mapping billions of galaxies, measuring how matter distributes across cosmic history. That data constrains dark matter models. Each new observation eliminates possibilities, narrows parameter space. Within a decade, we might know whether white holes work as dark matter or not. Then there's the information paradox. When matter falls into a black hole, what happens to the information it carries? Quantum mechanics says information can't be destroyed. General relativity says it disappears behind the event horizon, eventually lost when the black hole evaporates. Those statements contradict. Something's wrong with our understanding. Hawking spent decades on this problem. He initially argued information is lost, violating quantum mechanics. Later he changed his mind, proposing information somehow escapes through subtle correlations in Hawking radiation. But the mechanism remained unclear, the mathematics incomplete. White holes resolve this cleanly. Information doesn't get destroyed. It gets delayed. The black hole compresses matter to quantum scales where spacetime itself becomes granular. At that point, quantum tunneling creates a white hole. The information re-emerges, transformed but preserved. The process takes different times depending on your reference frame, creating apparent paradoxes that dissolve once you account for relativistic time dilation. From inside, the transition happens in microseconds. From outside, billions of years. Both perspectives are valid. Neither contradicts quantum mechanics or relativity. You just need to include quantum gravity effects that standard theories neglect. Critics argue this just moves the problem. Okay, information emerges from white holes. But how exactly does quantum tunneling work at Planck scales? What determines the transition probability? What happens to information during the bounce? Fair questions. Loop quantum gravity provides partial answers through detailed calculations of quantum geometry. But uncertainties remain. We're extrapolating physics to regimes 15 orders of magnitude beyond what we can test directly. That requires assumptions. Different assumptions give different results. Until we have experimental data, we can't be sure which version is correct. But here's what we can say. The white hole scenario is consistent with known physics. It doesn't require new particles, exotic fields, or modifications to fundamental laws. It emerges naturally from taking quantum mechanics seriously at gravitational scales. And it makes predictions we can potentially test. That's more than most quantum gravity proposals offer. Consider how scientific revolutions actually happen. They don't start with complete theories that explain everything. They start with hints. Anomalies that don't quite fit. Patterns that shouldn't exist under current understanding. Observations that force new interpretations. Then someone proposes a framework that makes those anomalies make sense. The framework is rough at first, incomplete, controversial. Critics point out gaps, demand more evidence, propose alternatives. Gradually, more observations accumulate. Some support the new framework. Some don't. The theory gets refined, extended, sometimes abandoned. Eventually, enough pieces fall into place that consensus shifts. What seemed radical becomes standard. We might be at that early stage with white holes. The hints are there. Unexplained gamma-ray bursts. Dark matter that behaves oddly. Theoretical calculations suggesting black holes transition. None proves white holes exist. But together, they create a pattern worth investigating. And the tools are finally becoming available to investigate properly. Gamma-ray observatories with unprecedented sensitivity. Gravitational wave detectors reaching new frequency ranges. Computational models that can simulate quantum geometry in realistic scenarios. Machine learning algorithms that can search massive datasets for subtle anomalies. We're entering an era where questions that were purely philosophical become experimentally accessible. Think about what confirmation would mean. Not just for astrophysics, but for physics generally. It would prove that spacetime has a discrete structure at small scales. That quantum mechanics and gravity merge through specific mechanisms we can calculate. That the universe operates on principles more subtle than continuous fields and smooth geometry. Every black hole in the universe would become a factory converting matter into white holes. Not immediately, but eventually. Stellar mass black holes would take longer than the current age of the universe. Primordial black holes might be transitioning now. Supermassive black holes in galactic centers would persist for googolls of years before quantum effects dominate. But the process would be inevitable, written into the fabric of spacetime itself. And those white holes would tell stories. Each one carries information about what fell into its parent black hole. The composition, the mass distribution, the angular momentum. That information gets scrambled during the transition, encoded in quantum correlations we don't fully understand. But it's there. In principle, you could reconstruct the black hole's history by analyzing what the white hole emits. In practice, that's probably impossible. The encoding is too complex. The quantum correlations too subtle. The signal too scrambled. But the fact that it's theoretically possible matters. It means the universe keeps records. Nothing truly disappears. Everything leaves traces, even if we can't read them. This connects to deeper questions about time itself. White holes challenge our intuition about causality and temporal flow. We're used to thinking of time as a one-way street. Past influences future, never the reverse. Causes precede effects. Entropy increases. But relativity shows time is more flexible than that. It can dilate, contract, even stop at event horizons. Different observers measure different durations for the same events. Past, present, and future don't have absolute meanings, only relationships that depend on reference frames. White holes take this further. They represent regions where time flows differently, not just in rate, but in character. An observer falling toward a white hole would never reach it, no matter how long they wait. Time itself conspires to prevent the approach. Meanwhile, from the white hole's perspective, matter emerges from a past that extends infinitely backward. The event has no beginning, only a middle and an end. These aren't paradoxes. They're features of how time works in curved spacetime. Our intuitions developed in flat space where gravity is weak and velocities are low. In those conditions, time behaves simply. One direction, steady flow, universal simultaneity. But the universe doesn't limit itself to conditions that match our intuitions. It explores the full range of possibilities that physics allows. White holes exist in that range, mathematically valid solutions to equations that accurately describe reality. The question becomes whether we're ready to accept what the math tells us. General relativity has never lied to us. When it predicted black holes, we found them. When it said gravity bends light, observations confirmed it. When it claimed time slows near massive objects, atomic clocks proved it. The equations don't care about our comfort level. They describe reality, and white holes emerge from those same equations through simple time reversal. Yet something feels wrong. You can't unbreak an egg. You can't unmelt ice cream. Thermodynamics insists on a direction, an arrow pointing from order toward chaos. White holes seem to violate this fundamental principle by ejecting organized matter from a region of maximum disorder. How does that work without breaking the second law? The answer lies in what happens at the boundary. A white hole doesn't continuously spew matter like a cosmic fountain. The emission occurs at specific moments, tied to quantum transitions that respect thermodynamic constraints. When a Planck star forms inside a black hole, it exists in a state of maximum compression. Not infinite density, because quantum effects prevent that. But compressed to the Planck scale, where spacetime itself becomes granular. At that scale, the rules change. Classical thermodynamics assumes smooth, continuous processes. Quantum mechanics deals in discrete jumps. An electron doesn't gradually slide between energy levels. It tunnels, appearing in the new state without traveling through the space between. The Planck star does something similar, tunneling from a black hole configuration to a white hole configuration. During this transition, entropy doesn't decrease. It gets redistributed. The information encoded in the black hole's quantum state transfers to the white hole's emission pattern. From outside, you see a sudden burst of radiation carrying all that scrambled information. The total entropy of the universe increases, just as thermodynamics demands. The white hole doesn't reverse time locally. It exploits quantum effects that classical physics can't account for. This matters because it suggests white holes could actually exist without breaking any laws. They're not perpetual motion machines. They're quantum objects operating on timescales and length scales where our intuitions fail. A white hole emission event might last microseconds from an internal perspective, but billions of years could pass outside. That temporal mismatch comes straight from general relativity. Nothing controversial there. The real controversy is formation. Black holes form through collapse. We see stars implode, observe matter spiraling into event horizons. The process is clear, well documented, understood. White holes require the reverse. Matter would need to explode outward from a singularity that somehow exists before the explosion. Playing that scenario backward looks absurd, like watching a supernova reassemble a star. But that's thinking classically. Quantum mechanics offers another path. A primordial black hole forms in the early universe, perhaps from density fluctuations during inflation. It's small, maybe the mass of an asteroid compressed into a volume smaller than an atom. Hawking radiation causes it to evaporate slowly, losing mass over billions of years. As it shrinks, quantum effects grow stronger. Eventually, they dominate completely. At that point, the black hole doesn't just evaporate. It transitions. The interior geometry flips. The trapped surface becomes an anti-trapped surface. The singularity that was in the future becomes a white hole singularity in the past. And everything the black hole ever consumed gets ejected in a single quantum burst. This isn't speculation without foundation. Loop quantum gravity provides detailed calculations showing exactly how this transition occurs. The math is complex, involving quantum geometry and discrete spacetime structures. But the conclusion is clear. A sufficiently small black hole will quantum tunnel into a white hole with probability approaching certainty. How small is sufficiently small? Roughly Planck mass, about 20 micrograms. Any primordial black hole formed with less than that mass would have already transitioned. Anything larger takes longer, with transition time scaling exponentially with mass. A solar mass black hole needs vastly longer than the current age of the universe. But a micro black hole formed in the Big Bang could be transitioning right now. That opens observational possibilities. Primordial black holes with appropriate masses would be exploding throughout the universe at this moment. Each explosion releases energy equivalent to thousands of nuclear bombs, compressed into a fraction of a second. That matches the profile of certain gamma-ray bursts. Short duration, high energy, no obvious source. GRB 060614 stands out as particularly interesting. Detected in 2006, it lasted for over 100 seconds, much longer than typical short bursts. But it showed no supernova signature, ruling out the standard explanation. And it originated from a region with very little matter, making other astrophysical sources unlikely. The energy output, timing, and location all fit the white hole explosion hypothesis. One event doesn't prove anything. We need statistics, patterns, predictions that distinguish white hole explosions from other phenomena. Researchers are developing those criteria. Specific spectral signatures that quantum geometry predicts. Gravitational wave patterns that accompany the transition. Correlations with cosmic voids where primordial black holes might accumulate. The search is complicated by how rare these events would be. Even if primordial black holes exist in large numbers, only those with precisely the right mass would transition during observable times. Too small, and they exploded billions of years ago. Too large, and they won't transition for billions of years to come. The sweet spot is narrow, making detection challenging. Dark matter adds another dimension. We know something massive exists that doesn't emit light. It holds galaxies together, bends spacetime, influences cosmic structure. But we haven't identified what it is. White holes offer a candidate. Tiny, dense objects that rarely interact with normal matter. They'd contribute gravitational effects without producing electromagnetic signals. Except when they explode. If dark matter consists partially of transitioning black holes, we should see occasional flashes as they convert to white holes. The explosion rate would depend on the mass distribution of primordial black holes. Too many explosions, and dark matter would be too energetic. Too few, and the hypothesis doesn't explain observations. But there's a range where everything works. This connects seemingly unrelated mysteries. Black hole information paradox, dark matter composition, quantum gravity effects, the ultimate fate of black holes. White holes touch all of them. They're not just curiosities. They're potential keys to understanding how the universe actually works at its deepest levels. Consider what it means for physics if white holes exist. It proves spacetime is fundamentally quantum. That general relativity, as successful as it is, represents an approximation valid only at large scales. That the true theory of gravity involves discrete structures we can calculate and predict. Every detection would constrain quantum gravity models, eliminating approaches that don't match observations. It would also change how we think about cosmic evolution. Black holes wouldn't be permanent. They'd be temporary stages in a longer cycle. Matter falls in, gets compressed, quantum tunnels, explodes out. The universe would be more dynamic than current models suggest. Regions we think are empty might hide white holes waiting to erupt. Voids in cosmic structure might actually be active zones where these transitions concentrate. Time itself takes on new character. We're used to thinking of cosmic time as flowing uniformly everywhere. But white holes break that uniformity. Their interiors connect to black hole paths through quantum transitions that don't respect normal causality. An observer inside would experience time differently than anyone outside. The universe's age becomes relative, depending on which reference frame you measure from. These aren't philosophical abstractions. They're concrete predictions that follow from taking loop quantum gravity seriously. If the theory is correct, white holes exist. If they exist, we can detect them. If we detect them, we learn how quantum spacetime behaves. The chain of reasoning is solid, built on established physics extended into new regimes. What happens if we never find evidence? That tells us something too. Either primordial black holes are rarer than expected, or the transition timescale is different than calculations suggest, or loop quantum gravity needs modification. Negative results guide theory just as powerfully as positive ones. Science advances by eliminating possibilities until only truth remains. But there's genuine excitement in the possibility that confirmation might come soon. We're not waiting for technology that won't exist for centuries. Current instruments could detect white hole signatures if they're occurring. Each new gamma-ray burst, each gravitational wave event, each anomalous observation gets analyzed for signs of quantum transitions. The universe might be showing us white holes already. We just need to recognize what we're seeing. Recognition changes everything in science. Once you know what you're looking for, patterns emerge from noise. Instruments designed for one purpose reveal unexpected phenomena. Data dismissed as anomalies suddenly becomes evidence. The search for white holes transforms how we interpret cosmic events we've been observing for decades. Every gamma-ray burst gets re-examined through this lens. Not all of them match standard models perfectly. Some occur in regions where no massive stars exist to collapse. Others produce energy distributions that don't fit supernova explosions. These outliers used to be filed as mysteries requiring better data. Now they're potential white hole candidates worth investigating thoroughly. The methodology is rigorous. You can't just point at something strange and claim it's a white hole. Each candidate requires multiple lines of evidence. Energy signature matching theoretical predictions. Location in regions where primordial black holes might concentrate. Timing consistent with quantum transition models. Absence of alternative explanations that fit the data better. Several events meet preliminary criteria. GRB 060614 remains the strongest candidate, but it's not alone. There's a subset of short gamma-ray bursts with peculiar properties. They last only milliseconds but release tremendous energy. No neutron-star collision in the vicinity. No supernova remnant. Just sudden, intense radiation appearing from seemingly empty space. Standard astrophysics struggles with these. White hole theory offers clean explanations. A primordial black hole finishing its transition would produce exactly this signature. Brief because the entire process happens quickly once quantum effects dominate. Energetic because you're releasing mass that's been compressed for billions of years. Locationally random because these objects drift through space independently of visible matter. The statistical approach matters as much as individual cases. If white holes exist at predicted rates, we should see certain patterns in the data. Distribution of burst energies following specific curves. Spatial clustering matching dark matter halos. Temporal frequency that changes as smaller black holes transition before larger ones. Preliminary analysis shows intriguing correlations. The number of unexplained short bursts roughly matches expectations if a fraction of dark matter consists of transitioning black holes. Their locations cluster slightly more than random chance would predict. Energy distributions show a tail that extends exactly where white hole models suggest. None of this constitutes proof. Correlations aren't causation. But they justify deeper investigation with better instruments. And those instruments are coming online now. The Vera Rubin Observatory starts full operation soon. It'll scan the entire visible sky every few nights, detecting transient events within hours of occurrence. If white holes explode at predicted rates, Rubin will catch them. Its sensitivity reaches faint objects that previous surveys missed. Gravitational wave detectors keep improving too. LIGO and Virgo already detect black hole mergers from across the universe. Next-generation instruments will reach smaller masses, down into the range where primordial black holes should exist. If a nearby black hole transitions to a white hole, the quantum tunneling process might produce detectable gravitational signatures. X-ray telescopes add another data stream. White hole explosions should produce high-energy photons alongside gamma rays. The spectrum carries information about what's happening during the transition. Different quantum gravity theories predict slightly different spectra. Observations could distinguish between competing models. What's remarkable is how quickly this field is moving from pure theory to observational science. 5 years ago, white holes were mathematical curiosities. Today, there are funded research programs searching for them. Conferences dedicated to detection strategies. Collaborations between theorists and observers working to match predictions with data. The pace reflects how much is at stake. Finding white holes wouldn't just confirm one theory. It would validate the entire approach of applying quantum mechanics to gravity. Every detection would constrain fundamental physics in ways we can't achieve through particle accelerators or other experiments. Think about what we learn from each confirmed white hole. The mass tells us about primordial black hole formation in the early universe. The explosion energy tests loop quantum gravity calculations. The timing constrains how quantum effects modify spacetime at small scales. The location maps dark matter distribution. One detection answers multiple questions simultaneously, and each answer opens new investigations. If the mass distribution peaks at certain values, that tells us about conditions during cosmic inflation. If explosions occur more frequently in galaxy clusters, that reveals how environment affects quantum transitions. If the spectrum shows unexpected features, that points toward modifications needed in current theory. This interconnectedness is what makes the search so compelling. You're not just looking for exotic objects. You're probing the fundamental nature of reality at its deepest levels. Every observation tests whether our best theories about quantum gravity actually describe the universe correctly. The philosophical implications run equally deep. If black holes don't destroy information but eventually return it through white hole transitions, causality works differently than we thought. Events aren't erased from existence. They're encoded, transformed, and released back into spacetime through quantum processes. Time itself becomes less absolute. Inside a transitioning black hole, time doesn't flow in the direction we experience externally. The interior connects to both the black hole's past and the white hole's future through quantum geometry that doesn't respect classical temporal ordering. An observer there would experience time in ways impossible to describe with conventional language. This isn't science fiction speculation. It's what the mathematics of loop quantum gravity predicts when you work through the equations carefully. The universe's structure at Planck scales differs radically from smooth spacetime. Discrete, quantized, with connections between regions that classical physics forbids. White holes make these abstract predictions testable. If observations match theory, we know the mathematics is capturing something real about nature. If they don't match, we learn where the theory needs refinement. Either outcome advances physics substantially. The historical parallel to quantum mechanics is striking. In the early 20th century, physicists developed mathematical frameworks that predicted bizarre phenomena. Particles behaving like waves. Uncertainty principles. Quantum tunneling. The math worked beautifully but seemed physically absurd. Then experiments confirmed every prediction. The universe actually operates according to these strange rules. Classical intuition was wrong. Quantum mechanics describes reality correctly, no matter how counterintuitive it seems. We might be at a similar juncture with quantum gravity. The mathematics predicts white holes, quantum spacetime, information preservation through cosmic recycling. It seems bizarre. But if observations confirm it, we accept that the universe works this way at fundamental levels. The search also highlights how science progresses through creative reinterpretation of existing data. We've been observing gamma-ray bursts for decades. Thousands of events recorded, analyzed, categorized. The data was always there. What changed is our theoretical understanding suggesting new interpretations. This happens repeatedly in science. X-rays were mysterious radiation until atomic theory explained them. Cosmic microwave background was antenna noise until cosmology revealed its significance. Pulsars were little green men until we understood neutron stars. The universe constantly sends us signals. We just need the right framework to decode them. White holes might be the latest example. The signals exist in our telescopes already. We've been recording white hole explosions for years without recognizing what they were. Now, armed with better theory, we can go back through archives, reanalyze anomalies, and potentially find evidence that's been hiding in plain sight. That's what makes the next few years so exciting. You don't need to wait for new technology or better instruments, though those will help. You can start searching immediately with data that's already collected. Every gamma-ray burst catalog becomes a potential white hole database. Every unexplained transient event becomes a candidate worth investigating. The community is mobilizing rapidly. Papers proposing detection strategies appear monthly. New collaborations form between research groups. Observing proposals get submitted to major telescopes. The field is moving from interesting idea to active research program faster than most theoretical predictions ever do. What happens when the first confirmed detection occurs? The impact ripples across multiple fields simultaneously. Astrophysics gains a new class of cosmic events to study. Cosmology learns about the early universe through primordial black hole properties. Particle physics gets experimental constraints on quantum gravity. Dark matter research potentially identifies a major component. The detection also validates a research approach. For decades, some physicists argued that quantum gravity is inherently untestable. The energies are too high, the scales too small, the effects too subtle to ever observe directly. White holes prove this pessimism wrong. Quantum gravity makes concrete predictions we can test with existing technology. That methodological lesson matters as much as the specific physics. It shows that fundamental theory isn't divorced from observation. Creative thinking about where quantum effects manifest can identify testable signatures. The universe is a laboratory if you know where to look. Of course, non-detection teaches us too. If extensive searches come up empty, that constrains theory just as powerfully. Maybe primordial black holes are rarer than expected. Maybe the transition timescale is longer. Maybe loop quantum gravity needs modification. Maybe white holes exist but produce different signatures than we predicted. Science advances through this iterative process. Theory makes predictions. Observations test them. Results feed back into better theory. The cycle continues, gradually converging on truth. White holes represent one turn of this cycle, happening in real time. The ultimate question is whether the universe actually contains these objects or just the mathematics describing them. We're about to find out. The observations are happening. The analysis is underway. The answer is coming. The search for white holes represents something deeper than hunting exotic cosmic objects. It's about testing whether mathematics alone can guide us to hidden truths about reality. Every equation that describes our universe could be telling us something we haven't discovered yet. Black holes emerged from Einstein's equations decades before telescopes found them. Now those same equations predict white holes with equal certainty. The question isn't whether the math works. It's whether nature bothers to implement every solution the math allows. Think about what we're really asking. Can information survive the most extreme compression imaginable? Does spacetime have a fundamental structure we can't see directly but can infer through quantum effects? Do black holes eventually return everything they swallow? These aren't abstract philosophical puzzles. They're questions with definite answers that observations could reveal within years. The evidence might already exist in telescope archives. Gamma-ray bursts we recorded but couldn't explain. Gravitational anomalies that didn't fit standard models. Spectral signatures that seemed wrong until quantum gravity gave them context. Science often works this way. The data arrives before the interpretation. Years pass. Someone proposes a new framework. Suddenly old mysteries make perfect sense. White holes force physics to confront its own assumptions about what's possible. We got comfortable thinking black holes are one-way streets to oblivion. That information disappears. That singularities represent true endpoints where physics breaks down completely. Quantum mechanics never accepted this. It insisted information persists somehow. White holes offer the mechanism. Not through subtle quantum correlations in Hawking radiation, but through explosive transitions that return everything at once. The implications stretch beyond resolving paradoxes. If primordial black holes formed in the early universe and transitioned to white holes over billions of years, we're watching cosmic recycling on the grandest scale. Matter doesn't vanish into black holes permanently. It gets processed, compressed to quantum scales, then released back into spacetime. The universe operates more dynamically than steady-state models suggest. Dark matter takes on new character in this framework. Instead of exotic particles we can't detect, maybe it's familiar objects behaving in unfamiliar ways. Tiny black holes scattered throughout space, some already transitioned to white holes, others approaching that threshold. They'd provide the extra gravity galaxies need without emitting light. They'd cluster in halos matching observations. And occasionally, they'd explode as quantum effects trigger the transformation. That explosion signature is what makes this testable now rather than decades from future. We don't need particle accelerators reaching impossible energies. We don't need spacecraft traveling to black hole event horizons. We need telescopes pointed at the right patches of sky when transitions occur. Current instruments have that capability. Next-generation observatories will have even better sensitivity. The timeline matters. Stellar mass black holes won't transition for timescales exceeding the universe's age. But primordial black holes formed during cosmic inflation could be reaching critical mass right now. The smallest ones transitioned long ago. Medium-sized ones are transitioning currently. Each explosion releases energy we can detect across cosmological distances. The universe might be showing us white holes regularly. We just haven't been interpreting the signals correctly. GRB 060614 stands as the leading candidate precisely because it breaks all the rules. Too long for a short gamma-ray burst. No supernova despite its duration. Originating from a region with minimal stellar activity. Every conventional explanation fails. White hole transition fits perfectly. One event doesn't prove anything, but it demonstrates the kind of signature we're hunting. Statistical analysis will ultimately decide this. Individual events remain ambiguous. Patterns across hundreds or thousands of observations reveal truth. If white holes exist at predicted rates, the data will show specific correlations. Energy distributions matching quantum gravity calculations. Spatial clustering following dark matter halos. Temporal patterns reflecting the mass spectrum of primordial black holes. Those patterns either exist or they don't. The answer comes from data, not theory. And we're accumulating that data rapidly. Every survey telescope, every gamma-ray satellite, every gravitational wave detector adds information. Machine learning algorithms scan for anomalies human analysis might miss. The search is systematic, thorough, and accelerating. What makes this moment unique is convergence. Theory developed enough to make concrete predictions. Observations reached sufficient sensitivity to test them. Computational tools emerged that can handle the massive datasets involved. all three requirements align now. That alignment happens rarely in science. When it does, discoveries follow. The broader lesson transcends white holes specifically. Extreme environments reveal physics we can't access through controlled experiments. The universe provides natural laboratories where quantum gravity operates, where spacetime curves beyond classical limits, where information undergoes transformations impossible in terrestrial settings. Studying these environments isn't just astronomy. It's fundamental physics conducted on cosmic scales. White holes exemplify this approach. They probe the intersection of quantum mechanics and general relativity. They test whether information is truly conserved. They reveal whether spacetime is fundamentally discrete. Every question connects to others. Every answer constrains multiple theories simultaneously. The philosophical dimension cuts equally deep. We're asking whether reality contains more than we directly observe. Whether mathematics points toward truths that observations haven't confirmed yet. Whether the universe implements every possibility physics allows or selects only certain solutions. These questions don't have obvious answers. Intuition fails at this level. The only reliable guide is following the mathematics wherever it leads, then checking whether the universe agrees. Sometimes it does. Black holes exist despite seeming impossible. Quantum mechanics describes reality despite violating common sense. The track record suggests taking mathematical predictions seriously. White holes emerged from the same equations that gave us black holes. The symmetry is exact. Time reversal transforms one into the other. If nature permits black holes, the math insists white holes are equally valid. The asymmetry we observe might reflect initial conditions rather than fundamental law. The universe started in a low-entropy state and evolves toward higher entropy. That arrow of time privileges black holes over white holes in formation mechanisms. But quantum transitions could bypass formation entirely. A primordial black hole doesn't form through collapse. It emerges from density fluctuations when the universe was seconds old. Its initial state isn't a star imploding but quantum foam crystallizing into spacetime geometry. From that starting point, quantum tunneling to a white hole becomes possible through processes that don't require time reversal. This distinction matters. You can't form a white hole by running stellar collapse backward. That violates thermodynamics. But you can form a black hole in the early universe, let it evaporate through Hawking radiation until quantum effects dominate, then watch it transition to a white hole through quantum tunneling. No thermodynamic laws broken. No causality violated. Just quantum mechanics operating at Planck scales. The universe might be full of these objects right now. Microscopic white holes that used to be primordial black holes. Too small to see directly but massive enough to affect their surroundings gravitationally. Occasionally exploding when quantum transitions complete. Each explosion releasing information accumulated over billions of years. That information returns scrambled beyond recognition. You couldn't reconstruct what fell into the parent black hole by analyzing white hole emissions. The quantum correlations are too complex. But the information persists in some form. The universe keeps records even when they're unreadable. This preservation matters for fundamental reasons. If information truly disappeared into black holes, quantum mechanics would be wrong. Not approximately wrong or incomplete. Fundamentally broken. The theory that explains chemistry, electronics, atomic structure, and everything quantum would fail at its core. That seems unlikely given quantum mechanics' perfect track record across every other domain. White holes offer an alternative. Information doesn't disappear. It undergoes the most extreme transformation possible, then returns to spacetime. Quantum mechanics remains valid. General relativity gets modified slightly at Planck scales through loop quantum gravity. Both theories survive with their core principles intact. The next decade will likely settle this. Current observation programs will accumulate enough data to either confirm or rule out white holes at predicted rates. If they're out there, we'll find them. If they're not, we'll know quantum gravity works differently than loop quantum calculations suggest. Either way, physics advances substantially. The search continues because the stakes are high and the prospects are real. We're not chasing phantoms or testing unfalsifiable ideas. White holes make specific predictions about observable phenomena. Those predictions either match reality or they don't. Science works when theories take risks like this. When they claim something definite exists in particular places with measurable properties. White holes exist in the mathematics with absolute certainty. Whether they exist in the cosmos is what observations will reveal. The universe has already answered. We're just learning to ask the question correctly.